Hello everyone. Today, we'll continue our study of bituminous materials. In the last lesson, we explained the classification, groups, and the colloid structure of asphalt. In this lesson, we will learn about the technical properties of asphalt. Asphalt possesses various technical properties, and today we will primarily focus on viscosity, plasticity, temperature sensitivity, adhesion, and durability. Firstly, let's dive into viscosity, which reflects the ability of bituminous materials to resist viscose deformation and external forces. The technical indicators that reflect asphalt viscosity primarily include penetration and viscosity. Penetration measures the viscosity of solid and semi-solid asphalt, while viscosity characterizes the viscosity of liquid asphalt. Factors influencing asphalt viscosity include its composition and environmental temperature. A higher asphaltene content in asphalt results in higher viscosity. Additionally, external temperature affects viscosity. Higher temperatures lead to decreased viscosity. Now, let's focus on penetration. Penetration is a key indicator for characterizing the viscosity of solid and semi-solid asphalt. It is one of the three primary asphalt indicators. Penetration reflects asphalt's resistance to shear deformation. Smaller penetration values indicate higher viscosity. In a specified temperature and time, a certain mass of standard needle recorded a vertical penetration of the depth of specimen. The size of the depth is the needle penetration. Penetration is indicated by the letter P with subscript TMT. We are to explain their meanings. P for degree of penetration, subscript capital T for test temperature, M for test standard needle mass, lowercase t for test time. Let's take an example. P25 degrees, 100 grams, 5 seconds equals 65 times 0.1 millimeters. The meaning of the expression is that the penetration test was carried out at 25 degrees using 100 grams standard needle, and the penetration depth of standard needle into asphalt was 65 times 0.1 millimeters. Where it is important to note that the penetration of the needle in units of 0.1 millimeters, then 65 pieces 0.1 millimeters is also 6.5 millimeters. Next, let's examine plasticity, which refers to asphalt's ability to deform under external forces without breaking. The main factors influencing asphalt plasticity are its composition and environmental temperature. Higher resin content in asphalt results in better plasticity, and higher external temperatures increases plasticity. Ductility is an indicator used to measure asphalt plasticity. The greater the measured ductility is, the higher the plasticity is. Ductility is also one of the three major indicators of asphalt. It reflects the total capacity of asphalt can withstand plastic deformation. First of all, the asphalt is made into H-shaped standard specimen. We see the right side of the top of this picture is the H-shaped specimens, and then placed in the specimen in 25 degrees water of the ductility machine, the right side of the certain. The two machines you see are ductility machines. The machine contains 25 degrees water. Start the machine and the specimen is stretched at a speed of 5 centimeters per minute, and The elongation is expressed by the length at break, expressed the unit in centimeter. We can see that the bottom picture on the right side shows the moment when the asphalt standard is pulled off, and the elongation measured of the asphalt specimen at the moment of pulling off, which is the elongation. Thirdly, let's explore asphalt's temperature stability, which refers to how its viscosity and plasticity change with temperature variations. The main influencing factors are asphalt composition, with a higher asphaltene content leading to lower temperature sensitivity. The key indicators for characterizing asphalt's temperature stability include softening point and the penetration index. Among them, the softening point is to reflect the higher temperature sensitivity of asphalt index. It characterizes the asphalt from solid state to viscous flow state when the corresponding temperature. The test method used for determination of the softening point is the ring and ball method. You see, the left side of this picture is the test instrument, the softening point instrument. The right side is the test personnel in the determination of the softening point of the test. Softening point is also one of the three primary asphalt indicators. The asphalt specimen into the prescribed size of the copper ring. The specimen placed on the weight of 3.5 grams standard steel ball. The specimen will be placed in the water or glycerin to 5 degrees per minute heating rate of water heating. When the water temperature is getting higher and higher, the asphalt specimen will be more and more soft, and a small steel ball placed on the top will fall down. When the asphalt softening down to 25.4 millimeters, the temperature is the softening point of asphalt. The penetration index is another crucial indicator for asphalt temperature stability. It reflects both the temperature sensitivity and the colloidal structure of asphalt. First, let's take a look at the basic principles. Engineers and researchers have discovered through extensive studies that the logarithm of needle penetration has a linear relationship with temperature. By measuring needle penetration at different temperatures, we measure the temperature as the horizontal axis and the logarithm of the measured needle penetration's values as the vertical axis. We have drawn a curve depicting the relationship between the logarithm of needle penetration and temperature. We found that this curve is a linear straight line. Within this linear straight line, the slope of the line, denoted as A, is a constant value. We refer to A as the needle penetration temperature sensitivity coefficient, calculated in accordance with the specified method. Pi equals 20 minus 500A divided by 1 at 50A, where A is the degree of penetration, temperature inductance coefficient. The calculation of the penetration index Pi, the larger the Pi value is, the better temperature stability of the materials. At the same time, the needle penetration index can also characterize the colloidal structure of asphalt. If the needle penetration index Pi is less than -2, asphalt for the soil type asphalt. Needle penetration index Pi is greater than 2. Asphalt for the gel type asphalt. Needle penetration index Pi in the -2 and 2. Asphalt for the soil gel type asphalt. Now, let's move on to adhesion, which represents the degree of adhesion between asphalt and the aggregates. Several factors influence the adhesion between asphalt and aggregates. Adhesion is related to the presence and the quantity of surface active substances on the asphalt itself. The more surface active substances there are on the asphalt, the poorer its adhesion to aggregates becomes. Adhesion is influenced by factors such as the acidity and alkalinity of the aggregates, the surface texture of the aggregates, and the amount of dust present in the aggregates. In general, alkaline aggregates exhibit better adhesion to asphalt than acidic ones, so we could prioritize the use of aggregates. Additionally, as the dust content in aggregates increases in simpler terms, when aggregates are more contaminated with dust, their adhesion to asphalt decreases. Adhesion is also affected by the moisture content in the aggregates. Higher moisture content in aggregates leads to reduced adhesion between the aggregates and asphalt. The evaluation of asphalt adhesion primarily involves two testing methods, the boiling water method and the water immersion method. The boiling water method is suitable for assessing the adhesion between asphalt and aggregates with the maximum particle size greater than 13.2 millimeters, while the water immersion method is suitable for assessing the adhesion between asphalt and aggregates with a maximum particle size equal to or less than 13.2 millimeters. Let's begin by discussing the boiling water method. 5 regular aggregates particles with a particle size ranging from 13.2 millimeters to 19 millimeters are selected, cleaned, and dried. A fine wire is used to securely attach the aggregates particle in the middle and immerse them in preheated asphalt, ensuring thorough coverage of the aggregates surfaces with asphalt. Subsequently, a test specimen is lifted, allowing the asphalt on its surface to cool. The aggregates particle coated with asphalt and then placed in boiling water for 3 minutes, and degree of asphalt film detachment is observed. Based on the extent of asphalt film detachment, adhesion is categorized into 5 levels, with level 1 being the poorest and level 5 being the best. Now let's take a closer look at the water immersion method. We begin by selecting 100 grams of regular aggregates with a particle size ranging from 9.5 millimeters to 13.2 millimeters, washing and drying them thoroughly, and then coating them with asphalt. Subsequently, the aggregates which have been coated with asphalt are placed in a temperature-controlled water base at 80 up and down 1 degrees, maintained for 30 minutes. The degree of asphalt film detachment is observed during this time. Based on the extent of asphalt film detachment, adhesion is categorized into 5 levels, with level 1 representing the lowest adhesion quality and level 5 indicating the highest adhesion quality. Fifthly, let's dive into asphalt durability. Durability refers to asphalt's ability to resist aging over prolonged exposure to various atmospheric factors, such as heat, sunlight, oxygen, and humidity. The aging process involves the gradual transformation of low molecular compounds within asphalt into higher molecular substances. During this process, the content of oils and resin decreases, while asphaltene's content increases. As a result, asphalt's flowability and plasticity decrease, while its brittleness increases. Several factors influence asphalt durability, including temperature and oxidation. Higher temperatures accelerate molecular emulsion and chemical reactions within asphalt, particularly when oxygen is involved. Aromatic asphalt transform into resins, which in turn become asphaltenes. Light and water also impact asphalt durability. When exposed to light, photochemical reactions occur, accelerating asphalt oxidation and increasing the presence of hydroxy groups and carbonate groups in asphalt. The oxidation and hardening of asphalt represent irreversible physical-chemical reactions. Evaluation of asphalt durability methods are mainly asphalt thin film oven test, rotating thin film oven test, pressurized aging vessel test, of which the asphalt thin film oven test and rotating thin film oven test, simulating the short-term aging process of asphalt, that is, construction scenarios in the asphalt construction heating process. Pressurized aging vessel test simulates the long-term aging process of asphalt, which also simulates the asphalt aging process in the natural world. This test, to varying degrees, simulates asphalt aging. We compare the changes of asphalt mass, penetration, softening point, and ductility before and after aging test to evaluate the durability of asphalt. It concludes our discussion on the technical properties of asphalt in this session.